Hi everyone, my name is Santiago and I'm here with Matthew to talk to you about Conduit, our best ever asynchronous parallel and distributed computing library. The compute library, in addition to supporting perfect communication, also supports a best effort communication model in which each node sends out messages at will and receives them as soon as they become available. It's a header-only C++17 and C++20 library. It's free software, open source by the MIT license, and freely available on github.com. As for its interface, it is uniform for inter-thread, and inter-process communication, which allows convenient over-decomposition. You can split your problem into different intercommunicating elements, each of which is assigned an inlet and an outlet, and then the interface connects them via a duct. The type of duct, be it inter-thread, or inter-process, is assigned at runtime by the library. The benchmark design consists of two problems. The first one is a graph coloring problem based on an algorithm after Leith et al. 2012. It's communication heavy because it's meant to assign channels to different access points in a Wi-Fi network. The second problem is a digital evolution problem using DISHNI, which is the digital multicellularity simulation we developed at the lab. This is more compute heavy and memory intensive. We have 5 different levels of synchronization, ranging from syncing on every update through syncing every certain time intervals to not syncing at all. And we also have an extra mode, which the processes are not aware of each other at all. As for the experiment, it consists of weak scaling with a fixed problem size for each CPU. We did 5 to 10 replicate timings, and the bars you'll see in the graphs are bootstrap 95% confidence intervals.
All right, thank you, Santiago. So now I'll take it over and talk you all through some of the highlights of results from our benchmarking experiments. So first, in the multiprocessing context for our graph coloring problems, this is across many different nodes in our cluster. What I've got for you here is updates per CPU. So this is how fast the CPUs are able to iterate through this graph coloring algorithm on the y-axis, and on the x-axis we have CPU count increasing left to right. And the first thing to look at is the performance of the implementation without any communication in between processes as expected. That performs consistently whether you're running it on 1 CPU or 64 CPUs. With our fully asynchronous run mode, so that's run mode 3 in red, we get about a little less than 2/3 the performance of running on 1 CPU when we're running it at scale on 64 nodes. And at 4, 16, and 64 nodes, we're getting significantly better performance for this asynchronous implementation compared to the synchronous implementation, which is run mode 0, shown here in blue. What we're looking at next is solution quality. So this is the number of graph color conflicts in the solution that was found by these algorithms. The first thing that jumps out is some inconsistencies in the performance of our intermediately synchronized run mode. So that's run mode 1 and 2. And so we threw a log axis on there so we can kind of still see what's going on with the rest of this data. And so on the y-axis is the number of graph conflicts, lower is better. And what was really interesting to us about this data is that at 16 and 64 nodes, you can see that the fully asynchronous run mode 3 actually yields significantly better solutions in the allotted time than fully synchronous communication in blue and no communication at all in purple. And so we're actually able to see some tangible benefits from this asynchronous model. So now we're going to move on to talk about the digital evolution benchmarks, again in the multiprocessing context. So we've got updates per CPU on the y-axis and node count on the x-axis. And at scale, at 64 processes, we're getting about 80% efficiency of our fully asynchronous run mode compared to what we're seeing at 1 CPU. At 16 and 64 CPUs, we are seeing significantly better performance of the asynchronous best effort model compared to the synchronous model. In fact, we're seeing about twice as much efficiency at 64 nodes for this asynchronous best effort model. And so kind of to tie this all together, what we saw was that, especially for large process counts, that the best effort communication model is yielding some really tangible performance gains for our benchmarks, and that a partial synchronization, which we included kind of as a control, has some inconsistent performance. And so we need to do some more thinking about how that's implemented and kind of its utility. And what was really exciting is, especially with that graph coloring problem, we were able to see that best effort communication not only improves the scaling efficiency, but also can yield tangibly better solution quality in a fixed amount of time. With that, I'd like to acknowledge Santiago, who's partnered with me on this project and been a major part of its development. I'd like to also thank our advisor, Dr. Charles Ofria, and another undergraduate who has contributed code, Catherine Perry. Here are the references for the models that we used for our benchmarks. And up here, I'd like to leave you with links to our full benchmarking data, which is available via the Open Science Framework, our library on GitHub, which has a big old README with a quick start to kind of get you started using the library if that's something that you're interested in trying out, and a link to our documentation for the project on Read the Docs. Great, thank you for your time.